thought I'd address cosmology and astronomy, because I've been talking about rocks, age of the Earth. Now it's time to look at stellar evolution, and it's time to look at Big Bang Theory, all that sort of stuff. Let's look at our solar system, any evidence for that being old, etc., etc. And let's have a across the board. Let's have a look at the universe in general. Evidences for one theory versus another theory, one model versus another model, and see which one fits the most observable evidence. So, okay, so we'll turn our attention to cosmology. Cosmology is a study of structure of the universe. That's the most simplest term for it. There is a definition, not cosmology, but cosmology, which is the study of the history of the universe. So they get confused. Observable evidence is used for cosmology, but when you're talking about the history, cosmology, that sometimes gets confused, and people start thinking that that's actually observable science. You know, it's not. It's just usually it comes down to the faith of the individual and what they want to believe. Okay, so where did all these histories come from? Ancient Greeks used to believe our universe was eternal. It had no beginning. It went on forever. So a lot of when we get to the different theories later on, you'll understand that ancient Greek thinking is still in the theories today. Okay, there's lots of stuff. There's okay, let's just say there's two main theories that were put forward based on the evidence that they were finding. As in, there was background radiation, microwave background radiation found, and things like that. And so they started putting through two theories. And so in the 1960s, the biggest popular theory was a theory called the steady state universe. Guys like Hubble discovered that things were moving apart, redshift, that the universe is expanding, and the distance, when you did the calculations, it's called the Hubble constant. It's a linear expansion rate, and they use when they're measuring stuff, they use scientists measure things in parsecs, not light years. Parsec is basically 3.26 light years. So there was a constant, Hubble constant, moving away by Hubble in about 1928, and this is what accelerated the theories. Yeah. So the steady state one. What is steady state? It is it's that the universe is expanding. So Hubble, that's what Hubble was seeing. So they came up with that. But they also believe the universe is eternal, and that's where you get the Greek thinking coming in. They have to have They have to have things which are really interesting. They have to create their own laws, laws of conservation, because if everything is eternal and it's expanding, then you're going to have a density issue. Density is going to be a problem. But for the steady state universe, they have to believe density remains constant. So what they do is they come up with this idea that matter can spontaneously pop into existence, but it can't be. No, it's not noticed. It's not observable. Okay. Otherwise, they'd have problems with the density as everything's expanding. Everything, the density would, yeah, would break the laws basically of the laws of conservation of mass. So, so conservation of like mass says that the amount should be the same. There shouldn't be any added stuff happening and all that sort of stuff. mass of the universe should remain constant. But they have to believe matter is being created but undetected. This makes the density the same. This has created their own little law called the law of conservation or of density. And this was popular, this whole theory, in the 1960s, for ages. Okay, but Big Bang, well, since the 1928, Hubble and all that. Anyway, Big Bang has come along with its theory, and it's saying the universe has a finite age, so it's saying it's not eternal. It's saying density decreases with time. That also means that temperature also decreases with time, and the discovery of the cosmic microwave background radiation is supposed to be, support it. Okay, right. So, yeah, there's a few issues. Big Bang has lots and lots of issues, and I want to get into them and really, really nail it. So I'm not sure where to carry on from. Let's have a look at just some actual things that you're supposed to really understand to get this. There's things called the Doppler Effect or the Doppler shift. You've got a light spectrum, and it goes from UV to ultraviolet to infrared along the spectrum. And when light rays are observed to be like on a radar gun when a car's being picked up for speeding, or sound coming off a moving object towards you, the waves are compressed. And so when we see light rays compressed, they go to the blue shift end of the spectrum. But when they go away from us, as in sound goes away from us, car goes past us, the light waves, the sound waves are expanded, and that shifts. With light, that shifts to the infrared part of the spectrum, the red shift. That's what's called red shift, the blue shift. Okay, and that sort of yeah. So that's all to do with the Doppler and all that. But the thing is, you got to argue. It's really, really hard to know if anything is redshifting, like galaxies are redshifting, or anything is moving towards you or away, because of the way they think about the Big Bang. When you if I move something away, like a galaxy moves away, its speed moving away from us, you should see it changing in the redshift spectrum, getting further along the redshift spectrum as it moves further away. And you could say, oh, we could calculate the speed it's traveling at, but you wouldn't know any difference by observation whether it is moving with velocity, moving away, or if the actual space in between us and the actual galaxy is actually stretching. And so there's a problem. Big Bang actually is about stretching the universe out. You say, what was before the Big Bang? Well, they don't believe when they think about the Big Bang, they don't believe there was any before, that there was any universe, any time, any space, nothing, any matter. And so when the Big Bang happens, they call it a singularity event, and there's heaps of different ones they use, but there's quantum fluctuation is one word they like using, occurs. And quantum fluctuation actually is just basically means nothing turns into something, and you could substitute that word with the word magic. Okay. Anyway, so a singularity event. So you could say this molten plasma thing that's the size of a proton comes into a singularity event. It just comes from nothing to something. And then it starts expanding. Now there is no nothing else. There is no space, time, matter, or anything. It's not an explosion as such. So it's not blowing up and all that. Because if it was, there would be a center, and then it would be like an explosion. So the Big Bang isn't quite. Calling it a bang is an interesting one, because it's not really even a bang. It's an expansion, really. So it expands, and time and space is created by the expansion. Now, you go, really? Yep. It's sort of how the Big Bang. So we'll go back into it later, but that's what they think of the Big Bang. Okay. So these theories are promoted. So as a Big Bang is going across and all this, and that's how it's working. Now there's a couple of misconceptions with some of the stuff that's being put out there, and that's one, the Big Bang, everyone thinks it's an explosion, and not necessarily correct there. And the other one is like space can expand, so the galaxy might not actually be moving further apart, but the space in between is. So you can't tell by observation if the time or the space is like the galaxy's moving or the space is stretching. Yeah. So if it is a galaxy actually moving at all, like is it actually moving, or is just space stretching? So that's debatable. Yeah, we do know it's moving apart though. That's one thing we do know, it's moving apart. Whether it's actually moving by speed or moving by stretching or both, it's really difficult to know. Anyway. So the Big Bang, anyway, it has this it has a few problems. It's taken over as being the preferred option, and that's mainly because of the cosmic microwave background radiation that's happened, which apparently supports it. But remember, the Big Bang model was made to explain the expanding universe. All right, so you can't say the expanding universe proves the Big Bang when the Big Bang was created to explain the actual thing. Okay, so yeah. So the only thing it's got going for it is the cosmic microwave background radiation. That's the only thing it's got going for it to support it instead of a static state universe and stuff like that. And what are we actually talking about here? This is I might have to explain what is the cosmic microwave background radiation, and why does it not support the static state universe, and why does it favor the Big Bang? Well, I'll go into that. I just don't know how long I'm going to talk for. So go into that later, and hopefully I'll try and explain every little part so you can really make intelligent, informed decisions based on you actually understand what the science is actually talking about. Okay. Now Big Bang has a few problems, but there are some issues. It has this thing called the horizon problem. Yeah. The horizon problem comes from the fact that the cosmic background radiation has a constant temperature. So when they look out in space and they're seeing all this cosmic... Okay, I'll explain the cosmic microwave background radiation a little bit. If you've got a fireplace and you've had a fire going, it's really hot, cooking, burning away, and then you put the fire out, the embers and the wood and all the stuff, as it starts to cool and go down, it starts going back to its cold state. That is the same sort of concept as the microwave background radiation. They think the microwave background radiation is the remnants of the energy that was released from the Big Bang, which was like the fireplace going, and now there's this embers that are still there, which is evidence to support that it happened. Okay, so that's what the microwave background radiation is. So anyway, but the problem is, everywhere they look in the universe at this evidence of it happening, it's using, I think it's Kobe data, it's constant. and that is a big problem. It's called the horizon problem. Okay, yeah. So temperatures, and so it's interesting. Imagine if you're at, if we're looking, if light's reached Earth from 13 billion years away, or light years away, and then on the other side of the universe, light has reached us from that side, 13 billion, and it's just got to us, but hasn't had time, so it's gone from 13 billion all the way to here, but hasn't had 26 billion years to get to each other across. So disparate parts of the universe the light hasn't reached each other. Okay. Now, but the problem is that actual temperatures are the same at both sides. So why are they constant? Why is it constant temperatures of this micro and background radiation when they haven't actually even the light rays haven't even reached each other from each side? That's like giving two people an oven, and ovens can go up to like, you know, trillion degrees Fahrenheit or Celsius, or say millions of degrees Celsius or something, and you've got, or Fahrenheit, and you've got two people, and they don't know what temperature each one is going to turn up, and they just turn it up to whatever temperature. That apparently all the galaxy, the micro and background radiation from all around the universe is all turned on at the same temperature. So why? That doesn't make sense. Okay, yeah, it's a problem, big problem. So anyway, I digress. So the temperatures are, yeah, basically the same. So light from each side hasn't reached each other yet. So why is the temperature still the same? If you get, you get hot and different temperatures, hot and hot, and they'll release the energy, and basically they'll become the same state. It's like hot water in a bathtub. It just goes throughout the whole bathtub, and the whole bathtub becomes the same temperature. It doesn't one part stay hot and the rest stay cold. It sort of verges. So how come, if light hasn't managed to be able to travel, the heat transfer can't have occurred between to make it constant for the background radiation? Hope that's clear enough. Anyway. So anyway, so they've never had thermal contact. That's a big one. And so how do you explain the same temperatures? So what they have is they have a really cool theory. Oh, that's good. So as the thermal little proton blah blah singularity event with the quantum fluctuation is occurring, so there's like all the plasma or stuff, as it blows up to apparently the size of a grapefruit. Okay, boom. Expand, sorry, because remember it can expand faster than the speed of light, and it gets to that size, and then apparently all the little mini galaxies are already things are already starting to exchange heat when it's the size of a grapefruit across the size. So that's the known size of the universe at this stage. So it's exchanging its heat in a small little grapefruit size, and so when it then goes boom, expands out to its massive size, it's already synchronized its temperature when it was a grapefruit size. Now, what science? What science led the scientists to believe this? No science, just faith. So we have a faith, a religion that's operating at this level already. Okay, no science involved there. They're just trying to somehow fit the data, their model, to the data, and coming up with weird and wonderful applications to do that. Okay, second problem with the Big Bang is there's a flatness problem. Gravitational potential energy moving when it, like water going down a dam, when it hits the bottom, its gravitational potential energy can move to kinetic energy. Okay, so the problem they've got is the gravitational potential energy in the universe versus the moving kinetic energy. It's supposed to change in the lifetime of the universe. To solve the problem, it kinetic gravitational ratio, it should be observed to be heading towards 1. If it's near 1, it's supposed to head towards. If it's near 1, it is supposed to then go towards 0, and if it's not near 1, it's supposed to go off into infinity. Mathematically, I personally don't understand it at that point. But anyway, the observing it is actually near 1, but it hasn't moved towards 0, and that is one of the problems they have. One of the things they are finding it hard to explain. I mean, I'm finding it hard to explain. So it's the grapefruit expansion, wonderful, wonderful manipulation of science there, with no real science, just beautiful belief system, make-believe system, I should call it. Okay, so to solve this problem of the gravitational potential energy, going to kinetic energy, etc., etc., they had to come up with this thing called, like this whole thing, what I talked about, the grapefruit and all that, that's called inflation theory. It's the suggested theory to solve the flatness and all that, and the background radiation, etc. Horizon problem was the inflation theory. So the universe starts off as the size of a protein, it expands to the size of a grapefruit, and so while it was really tiny, it allows all the universe to contact and exchange thermal contact with each other, and then it goes big. Okay, so that's the inflation theory used, which is accepted theory that says why the what they observe, how it can fit their Big Bang theory. Okay, otherwise it doesn't fit the Big Bang theory. The Big Bang theory, its predictions, what will happen? Well, while it keeps expanding, it's going to keep expanding apparently, and then at some stage gravity itself is going to pull it back together, and then it's going to compact down into a big crunch, and then some theorize that it's going to rebound out again and do another Big Bang. This is getting straight back to the Greeks' idea that the universe is eternal. It's basically doing the same thing. Okay, so is there science behind any of this? No. No. Okay. Yeah, so what about this universe we're in? Only 6% of the universe is light matter. That's us and dirt and planets and stuff. So that means that 94% is invisible matter. Can't see 94% apparently. It's thought to be dark matter or dark energy or something. Anyway, you know what? I've already explained quantum fluctuation, but yeah, these are all things theorized. They've come up with some really weird theories actually to explain a lot of things. What causes a quantum fluctuation? Things like string theory have been promoted, which is talking about mini verses and all that, like little other universes. Yeah, to try and explain lots of the stuff they don't know. Anyway, in the last 25 years, the Big Bang model has had all these new things added to it. So when was it ever 100? Were they 100% convinced Big Bang theory was correct 25 years ago? Yes. Okay, so what's happened in the last 25 years? Okay, string theory has been added to it. The idea that there's multi-dimensions to the universe. Dark energy is being promoted. There was no inflation back then. Okay, so that inflation theory with because of the background microwave because of the horizon problem and all that, that's it wasn't there. Dark matter. The Hubble constant's changed. It was it's 50. It's gone from 80 to 50 or 50 to 8. Yeah, 80 to 50. So that's changed, that constant's changed the actual age of the universe significantly, down to about 13.6 billion years now. That's a big thing that's changed. The Hubble constant's changed. Think about that for a second. The Hubble constant has changed. It shows you how amazingly constant things are in science. Anyway, basically, when you think about it, with all those added changes, it's actually an ad hoc theory with no way to falsify it, because every time something comes along, it just changes itself to fit the new evidence. So they were 100% convinced in 1980, that was sweet. Now they're 100% convinced it's correct now, but nothing has actually remained the same, really, except the sort of outline of it. All the details have changed in the theory since then. So when was it ever a fact, or 100% perfect, or 100% everyone 100% convinced all the time, even though it's totally changed in 25 years? Come on, does that not show you that it's a massively got massive issues itself? Okay, I think you've got to think, hang on a minute, if everything has changed in the theory and they've just basically kept the name and sort of the outline idea, is it 100% going to be right in another 25 years? I would doubt it. Well, let's have a look at the evidence for different models. That's about 26 minutes, so I really want to go a bit faster. Okay. Let's have a look at the evidence. Let's look at our actual age of our solar system and look at the models and weigh up the different models, which one fits. Okay, so you've heard a lot of things about history, where things have come from. Now let's look at actually creation model, because God made it not in millions of years, He made it in days. Okay, so we're not trying to fit things down to thousands of years. We're trying to fit things down to days being created, and the age of the universe being around 6,000 years old. Okay, no millions, billions, or anything. So the differences in the theory is incredible. So which model fits? How old is this? I mean, you've got to think, how old is this universe? How old is the solar system? You can find evidence supporting billions of years, then it goes against what the Bible's saying clearly. So you've really got to be able to prove it. And Christians have to be able to defend their faith, because evolutionists are pushing their faith. So which is true? Okay, so let's look at the moon in our solar system. Its gravity, moon's got a gravity, Earth's got a gravity, and they're pulling against each other. And it's moving away from the Earth about 4 centimeters per year. Okay, but biggest problem is if you start adding lots of time, like millions and then billions of years, that means in 1.4 billion years it was actually contacting the Earth. So that is doesn't fit the model at all, because they think, they've said, oh, we sampled moon rocks that are 4.6 billion years, around the 4.1, 4.2, 4.6 billion years age. Well, the moon would be it's just crazy. Okay, so that's a big problem. So which model does it fit? The moon's recession. It fits the young Earth model, not the old evolutionary model. Comets. Let's look at the other thing in our solar system. Comets, observable comets. They've got two types: long and short period comets. So the question is short period, and they're mainly made up of ice and stuff like that, and they basically disappear after a while, because every time they go around the sun, they start melting, lose a bit of their part of their comet. Now they're not all ice, I guess. So people would say, oh, they're not all ice. Yeah, but that's what the tail of the comet is when you're seeing it. You're seeing it. The tail. It's bits that are coming off. Okay, so why are there comets then? If they're billions of years old, the universe or our solar system, why are there still comets? They should have all just gone, melted and disappeared and disintegrated by now. So they come up. Scientists came up with the Oort Cloud, the special, unobservable, no evidence required Oort Cloud. It's apparently a ring of comets that keeps the long period comets coming. This is for long period comets, okay? So apparently there's this unobservable, no evidence Oort Cloud, and the only reason why they believe it exists is because it's the only thing they can come up with that gives them a reason why there are long period comets. Think about that for a second. They're believing in something they can't observe. They just believe it exists because it. Otherwise, long period comets points to a young solar system. So the evidence points to a young solar system, but they would choose rather to believe in something they can't observe. They just believe it exists. That is called religion or faith. Okay, believing in something you cannot observe, etc., is faith. Okay, so scientists remember that they don't want to believe in the young solar system, so they'd rather come up with the Oort Cloud. Okay, and there's the Kuiper belt, which is about around Neptune, with which is supposed to make the short period comets. Okay, so where do the short period comets come from? Apparently from this Kuiper belt. Comets in this belt, though, are huge. They are humongous, and never have been observed comets that size going around. So we only see like small ones compared to them ones that shoot around. So there's no real reason to believe that they're actually the reason for short-term comets. No real reason apart from faith again. Okay, next thing. That's comets. That's evidence, observable evidence point to, yes, young. The moon point to the young. What about the sun? The sun. It's a big thing in our solar system. Age of the sun. It's the sun. Let's talk about the sun. It's a thermonuclear fusion. It's huge going on. Supposedly it came to life 3.5 billion years ago. Okay, so its age and all that. Yeah, what happens with fusion? Probably worth explaining. As the sun gets older, the sun's supposed to get brighter with age. So if it was 4.5 billion years old, like they think it might be, it should be 40% hotter, okay, than it was at the beginning when it first was a sun. So as it gets older, because of the few nuclear thermic reactions, it will get hotter. So yeah, so it's supposed to be 40% hotter now than it was when it was first sort of made itself. So what the average temperature at the moment is 59 degrees Fahrenheit or 15 degrees Celsius. Okay, and that's basically what they think for a long time has been the average, 15 degrees Celsius or 59 Fahrenheit. So think about this. We'll do some maths here because this is quite interesting. If the sun gets hot, with age gets hotter, so it's 40% hotter now than it was then. It's 15 degrees Celsius now, and life apparently supposedly came 3.5 billion years ago on our planet. That means the sun is 25% less brighter, so the temperature it works out to be is 18 degrees Celsius or 32 degrees Fahrenheit cooler. Alright? It's when life apparently was supposed to have evolved here. Okay, so that's going back with saying the sun's old. That means the average temperature on our planet is 27 degrees Fahrenheit or -3 degrees Celsius, which is below freezing. And this is actually a real problem for evolution, biological evolution, because it's saying it needs heat for evolution and all that to happen naturally, apparently, in their theory. Okay, so it's below freezing for them. Okay, so it's a real problem. So let's look at some 5 different evidence just now for our solar system and age and all that, because let's hit this astronomy. The recession of the moon. Yep, that it can't be more than 1.4 billion, otherwise we would have contact. Comets themselves, observable comets, shouldn't be around unless there's a long-term ones unless there's a miraculous unobservable Oort Cloud, which doesn't exist, remember. It's all about science, not wish we had a Oort Cloud. Okay, so comets point to a young universe. Age of the sun itself. Let's go into that. Okay, and supernova remnants. The age of the sun itself has some quite big problems as well. I want to look at that, but fourth one, supernova remnants, and we'll have a look at that. Okay, so it's about stars again. Supernova remnants are stars which are doing their thermonuclear fusion. When that happens, it's converting its hydrogen into helium, and then it goes into carbon, then into oxygen, then into iron, and that's when the fusion process stops, and the star starts to gravitationally collapse in on itself. After it starts to gravitationally collapse in on itself, it's going to trigger a supernova. That's what supernova is. Okay, so as it's gone through its thermonuclear reactions all the way to the end, that's when it's gravitationally going to collapse and supernova out. Okay. Now, so supernova is short for SNRs. Okay, and the remnants is the gas in the cloud that's supposed to be left over from the explosion. Okay, so they're thinking these stars have gone through their thermonuclear, collapsed, and then exploded, and we should be able to see these remnants. That sounds plausible, doesn't it? Okay, has it been observed? Yes, we have actually observed a supernova. In 1054 AD, it was observed by the Chinese Crab Nebula explosion. In 1604, Galileo and Kepler actually observed one, and in 1980 we observed another one. So they have been observed. So it's observable evidence. This isn't just theoretical astrophysics or anything. You know, this is happening. This has actually happened. Okay, so what is it? Supernova remnants, though, are divided into 3 stages, 3 different ages, basically. Stage 1, it's just after they're exploded, within a few hundred years, basically. That's called a stage 1. The supernova just happens from it explodes, and then hundreds to thousands of years later, since the explosion, that would be a stage 2. And then a stage 3 would be if it's like millions of years ago it's exploded, and you're seeing the remnants of it. So they've got 3 sort of ages of the supernova explosions of the stars. And so evolution, every model, a Big Bang or evolution model, predicts that you'd find at least 2 stage 1, about 2,260 stage 2, and about 5,000 stage 3, based on the 13.6 to 20 billion year old galaxy universe. Sorry. Okay. Creation model, though, which predicts a young universe, predicts there will be about 2 stage 1 and maybe 125 stage 2, but no stage 3, because they don't believe in millions, the millions of years. So that's interesting. Okay, so observationally, what actually scientifically has been observed, they've seen 5 stage 1, 200 stage 2, and no stage 3. So this actually fits the supernova remnants. Actually fits the young universe model. Okay, now let's look at a bigger one. So we looked at moon, stars, comets, yeah, and they're all fitting the young model. So yeah, crazy, isn't it? Okay, let's look at galaxy formation. Now, if you're an evolutionist here, you'll be sweating. You'll be sweating because, oh man, and you have problems, big problems. Okay, wait till I get to the stars. How stars are formed. Anyway, galaxies haven't been observed, okay, to form or anything, um, and they have different. But if you look at just galaxies and you're not sure, even if you're not worried too much how they're formed and all that, but we just look at their shapes and stuff. We have spiral ones, and because of the way they're rotating in the spiral pattern, um, they should have lost their shape if they're old. So basically, spiral galaxies shouldn't exist if they're after 1 to 2 billion years. That's the that seems to be the mathematics of it. But when they look at the supposedly oldest galaxies, they're still spiral shaped. So scientists don't actually know how a galaxy forms anyway in the first place. But just looking at their shapes shows they can't actually be that old. Okay. Now stars. What about stars? So far, everything so far is falling, isn't it? Everything is falling to young Earth model observation. So you think, why are there evolutionists who believe in long universe ages? Yeah, hopefully you're getting the picture. It's a belief. It's a faith. It's not about evidence. We'll choose to ignore evidence because the evidence is glaringly obvious in favor of a young creation model. Okay, so origin of stars. The popular theory, will be insane for you, is that vast clouds of gas and dust. Okay, you got these gases and dust, and the gases are basically trapped around the dust, and because of gravitational contraction, and that's a fancy way of saying when gravity, because of these things have a lot of mass, the dust and the gas, the gravity formed from the mass contracts it all, pulls it all together, and collapses it in on itself, and it becomes turns into a star. That's the star called a protostar. Okay, so it's the gravity acting on the gases in the dust to pull it together, and then it collapses into in on itself, and that starts this is called a protostar. Then the gas and dust becomes so hot that the nuclear fusion actually starts, and that's when the star is born. Now that sounds really easy, plausible, wow, amazing, okay? But every scientist, you get a scientist to get gas and try to get it to collapse in on itself. Good luck with that. Okay, so what is actually happening there? Let's have a look at this problem with this theory. Okay, gas, when it starts to gravitationally come together, which it can, the gas starts to heat up, as it would, because remember it has to heat up to a certain point to get the nuclear fusion anyway. So it starts to heat up as it comes together, as it starts to contract, but it causes heat, and heat pressure actually makes gas expand, not collapse. So it goes against itself. So when it starts to come together gravitationally, it starts to heat up, but then the heat pressure actually expands it, and that is actually what is observed. So there's a huge problem there, isn't there? So how do they have to get it to happen then? If they know this is what happens, the heat actually expands it, then how do they get past it? See, they've got to overcome the heat expansion with tremendous pressure to get it to collapse in and on itself, for gravity to take over. Okay, so yeah, what's actually observed though? Gas is not contracting, but spreading out. The critical size needed for gravity to take over is not observed. Okay, so there's a problem. So interstellar cloud collapsing by gravitationally is a problem in science. So, stellar formation, the interstellar clouds collapsing by the gravity, making it into a wonderful star. is just a good idea, but they haven't observed it. And they wouldn't observe it anyway, because of the problem. If this was the way a star was made, it would take thousands of years, probably theoretically, for that to happen anyway. Okay, so it's never been observed forming, nor has the actual process of the collapse, and that is a real issue too. So other problems with stars forming like that, by gravitational collapse, the central fugal in rotation, there's an issue there. And what about magnetic field pressures? Lots of issues to overcome, and again, not, scientifically observable, etc., etc. So when you get these large, say you got these large things of gas out in the universe, what are they? They're called nebula. Large amounts of gas and cloud dust and all that, that's a nebula. Okay, so when they chuck out that fancy word nebula, that's what they're talking about. So what is all this? This is all this. We believe it happened this way. A star is formed, stellar evolution. We believe a galaxy happened this way. Okay, we believe. What is this? This is unsupported dogmas, and this is in present day astrophysics now. This isn't like in the 1700s, 1500s or anything. This is modern day astrophysics with its dogmas that are completely unsupported, and is being passed on as a theory, and they're actually misleading people and deceiving people by omitting, by omission. Deception by omission is actually, that's not presenting the evidence, is not really constitutes a theory. Okay, so astrophysics, get your act together. Okay, now people have said, well, we observe in the universe, we've observed star nurseries, and basically they'll promote in the big magazine articles, we've found a star nursery where stars are born. We've got it, evidence, observational. We've proved our stellar formation, evolution theory. Okay, so they proposed that Eagle Nebula. Remember what a nebula is? It's like gas and dust and all that. So these giant clouds that look like fingers, okay, the big dark gas nebula. What's actually happening is there's different types of nebula, and they're hitting against emissions nebulas, and as they hit, these nebulas hit, they basically go up, and that's what we see. These form these big gas clouds that look like fingers. Okay, so anyway, they've said no, Eagle Nebula is not a star nursery. Okay, so that one's gone down. Okay, what about the Horsehead Nebula? That was promoted as well as a nice little star nursery. Is stars forming there? No, they're actually expanding. Okay, they were promoted as we can see them forming. No, they're actually expanding when they were believed that they were actually forming stars in the past. Now they know that's been disproven. It's not a star nursery. Okay, and I would hazard a guess that every star nursery is actually just gonna have the same issues, just because you can't see it expanding at the moment because of all the dust blocking the view. Is going, basically it's going to be a point where they're gonna say no, we can't see it. But let's utterly put the nail in the coffin for star formation. Let's just utterly nail this evolutionary, what's passed as science. Let's nail it, put a nail in the coffin. I can disprove it. Okay, mathematically, let's put it to the test. Now, there's been they've reckoned they found 100 billion galaxies, 10 to the power of 11. Each galaxy has an average of 2 billion stars, 2 times 10 to the power of 11. Okay, so 2 billion stars, 100 billion galaxies. Okay, 10 to the power of 11, 2 times 10 to the power of 11. Okay, if you say the universe is 20 billion years old, remember they're saying it's 13.6, and they're pretty sure, even though they've changed it heaps, God, they're just so dogmatic. Anyway, The mathematics shows us that there needs to be 1 trillion stars needed to form every year. For 100 billion galaxies, 200 billion stars within 20 billion years. Not a hard mathematics to do. That's 100 billion times 200 billion divided by 20 billion gives you 100 trillion stars that have to form. 100 trillion stars have to form every year for 20 billion years to get the numbers that we have currently observable. That's, let's break it down to, that's 2.7 billion stars per day, or for 20 billion years. That's not 2.7 billion stars per day for one day. That's every day for 20 billion years, or 31,700 stars per second. 31,700 stars per second for 20 billion years. So how many have they observed forming? Not one star has been observed forming. Wow. Got a problem with your theory, I would say. So evolutionists, you know, how do they get past this? They say, well, we believe all the stars formed in the first million to maybe 200 million years after the Big Bang. All of them formed together around that time. Okay. Okay, so that's why the evidence that we see today does not support your model. So you come up with a way to try and explain it away, which has no actual scientific valid reason. Okay, sure. But the evidence again doesn't support your model. So anyway, let's just move on with the evidence, because every time the evidence doesn't support your model, you come up with the Oort Cloud, you come up with the grapefruit size cosmic background radiation thermal exchange. Okay, and now you're coming up with all the stars must have formed in the first 200 million years, because they aren't doing it now. Okay, sure, we'll give you that. Let's look at cosmic background microwave radiation again. Let's have a look at it. Apparently, supposedly left over from the heat from the Big Bang. You know, like a fire's embers that are going out. Has the Big Bang got, what evidence has it actually got to support its billions of years? Like, let's look at it, because it's kind of flaky. Okay, so it has the redshift. Okay, that's to support it, a redshift factor, the cosmic background radiation, amount of elements there are, the abundance of elements, and the only other support it's got is the media and the education system. That's really it. So let's have a look at some of this. Let's break down the Big Bang into its like actual meaningless nothingness, silly stupidity. Okay, a flaming ball of plasma from nothing, a hypothetical mass of energy of time and space is ripped apart, exploded, expansion of time and space, not the blowing up dynamite. Okay, there is no center, and this might shock you, there is no center to the universe based in the Big Bang Theory model, because all the galaxies on the edge of, because they believe all the galaxies are on the edge of the universe. If they believe there's no center, and you go, what? How can there be no center? Remember, it's not an explosion; it's an expansion. So think of a balloon with dots on a balloon, and the dots on the balloon are the galaxies. Okay, so you've got to get really creative to believe the Big Bang. Okay, so I'm doing my best to explain it. So you put dots on a balloon, and you blow up the balloon, and as it's expanding, the time and space in the universe is expanding. On the outside of the balloon are the galaxies. Okay, so that's how it's working. Nothing's inside the balloon. So there's no center as such. Okay, so that's what they say. There's no center, and this is what's happening. It's very important. That concept. Okay, we'll get on with. I'll come back to why that's important for them. Okay, so it blows up. Blah blah. It's got a word called homogeneous. everywhere in the universe it should look the same. Okay. Now, why is this? This is because of a guy in 1543 called um, Copernic, Copernic, Copernicus. Yeah, I think that's it. Anyway, he said that the Earth is not the center of the universe, and he got labelled a heretic for that one, as you would. Anyway, that Copernicus, he was right for sure. But the thing is, they've used his idea as an actual model now. It's called the Copernican or cosmological principle, that it states there is no special place in the universe. We are not in a special place. Its conclusions are basically that the universe appears all the same in all the directions viewed from any point in space. There is no spatial spatial location, spatial location in the universe. Okay. Now that's why the Big Bang has no middle, okay, because of the idea, no specialness, etc. But when we look at redshift, remember redshift is supposed to be one of the things that is in favor of the Big Bang, but when we look at it, we see a problem. Remember the light spectrum has UV, which is the blue, it goes to the green, yellow, and then over to the other side to the infrared, the red. So blue to redshift, okay? Ultraviolet to infrared. It moves away. If it's moving towards you, you'll see light rays compressing or moving away, expanding. So ultraviolet to infrared. Light waves are compressed when moving towards you, so they show up on the blue side. In the blue wave, they don't turn blue, they show up on the blue wavelength area, and then when they're moving away, they stretch apart, so they show up in the spectrum on the red side. Okay, that's redshift. Okay, so that's in favor apparently with the Big Bang. But let's look at that really carefully. Let's think about it really carefully. If I'm looking from a telescope from Earth and I look at a galaxy, and then I look at another galaxy, I will see on the redshift, if it's moving away, whereabouts, how far away it is. If it's further away, it will have moved along the redshift spectrum more. So you'll be able to see distances of these galaxies. Okay? And what actually is observed is really against absolutely a nail in the coffin for the Big Bang Theory. In fact, this should be the absolute end of the Big Bang, and show that it's just pure faith. Big Bang predicts that we should see galaxies in all places along the redshift spectrum, because it's all supposed to be all the same no matter where we look. But what is actually observed is distinct quanta. It's a measurement. It means 1 million light year intervals. It's like a quotient. Is a distinct length, sort of. Okay. Anyway, what we seem to be seeing is from Earth, though, when we look out, there's actually distinct quanta. Quanta. Can't say very well. Anyway, what we seem to be seeing is these concentric circles of galaxies around our galaxy. Not what we should be seeing if the Big Bang's correct. What's actually really amazing is the redshift distribution shows strongly quantized measurements, that's 100 million light years, in a galactic centric frame of reference. That's a fancy way of saying basically from our galaxy we look out, and every 100 million years, 1 million light years intervals, we see galaxies, and then we look out further and then we see another 100 million light years, another group of galaxies, and then we look out again 100 million years, and they're all systematically going out from us, our galaxy being near the center. That's actually what's observed. We're not talking about geocentric, where Earth is the center. We're talking about galactic centricity, that our galaxy seems to be the center. How far, how close to the center does it have to be for the observable evidence? it has to be within 1 million light years of the center for us to have our observations what we've got. So we seem to be within 100 million light years of the center of the universe based on redshift. Is redshift supporting the Big Bang? No, it's supporting that we're in a special place in the universe, and it actually goes against the uniformed, homogeneous, the universe looks the same, which is what the Big Bang is actually implied. Yeah, so we are in a special spatial place, location in the universe. Nail in the coffin. Hopefully we've looked at it. We've looked at location, we've looked at star formation, galaxies. What about galaxies? We looked at I didn't look at the star light, but just think, if we are in the center, our galaxy's in the center, central galaxy centricity. If we're in the center, basically, that means the mass of the universe, we're in the focal point of the mass of the universe, so we're at the highest gravitational point, our galaxy. Now what does that mean? That means that we know that time can be slowed or affected by acceleration and gravity. So this is interesting because we believe 6,000 years age. If we are in a gravity eccentric position, which in gravity affects time, it's called time dilation, then gravity affecting the time on us means the time is can be slowed down by gravity. But on the outer edges of the universe, less gravity affecting the time. What does that leave us with? Well, it leaves us with the fact that you can have thousands of years in one place as everything is expanding, and on the outside billions of years because of the gravity of effect. And Bible says that God stretched out the heavens. That's why they were stretched out. That's why we see this moving apart, the shifting. That's why if we're near the middle, there is we are in a special place because of that reason. He put us there. Yeah. Evidence. Okay, so there's moon recession, the stars, the comets. I mean, you could go into the volcanic eruptions on Titan around Jupiter. You know, it's just so much evidence for a young solar system. We've looked into star formation, star remnants. Yeah, we've looked into different redshift, star formation, the time needed to form all the stars within the 20 billion years. That doesn't work. What about star nurseries? We looked at that. We looked at origin of stars. No. Looked at supernova remnants. That's in favor of young Earth, comets, and galaxy formation, etc. What else is there to look at? We've looked at everything we can look at, and everything points to this universe being young and not the Big Bang model.